Okay, this is the first part to to our final review. For number 1, they're asking us to simplify and to state the excluded values. I'm not going to worry about the excluded values part, but they're talking about any scenario where you would be dividing by 0. So if our input was going to be 0. In this first one here, when they have n plus 6 over 5n squared plus 30n, we're looking for how we could factor out this part here. You guys are used to seeing the quadratics and then writing it as like the product of two binomials. What I mean by that is like a x plus 3 times x plus 4 after it's been factored. In this example here, we want to find the factors, or the greatest common factor between the 5n squared and 30n. I can write the denominator like 5n times n plus 6, and it's all over n plus 6. Now that I've got the n plus 6 in the numerator and the denominator, these two are going to divide. In the numerator, I'm going to be left with 1, so this is 1 over 5n. In number 2, we have m plus 1 divided by m squared minus m minus 2. In here, we're looking for two numbers that have a product that multiply to -2, and two numbers that sum or they combine to -1. So I could write this like m plus 1 in the numerator, and it's m plus 1 times m minus 2. Just like the last one here, when I divide m plus 1 by m plus 1, I'm left with 1 in the numerator. This is equal to 1 over m minus 2. In number 3, whenever we're trying to add or subtract the fractions, I need a common denominator. So if you had 3/4 take away 1/5, I would need to figure out what the denominator should be. Some people just multiply like 4 and 5 together. In this case, that would actually work for 20. The same idea here. If I have an x minus 1 and an x plus 5, I want both of these denominators to be x minus 1 times x plus 5, which you don't have to write as the two different denominators in here. So to get the x plus 5 in the denominator, I need to multiply this fraction here by x plus 5. So it's like 4 times x plus 5. And then I'm multiplying 4x times x minus 1. So 4 times x and 4 times 5 is going to be 4x plus 20. Here I'm multiplying 4x times x squared, x to get x squared, and I'm taking away 4x. But I still am subtracting, so I'm going to include the parentheses. And then all of this is going to be divided by x minus 1 times x plus 5. So here, I'm going to rewrite this as after I distribute the negative. So instead of taking away 4x squared, I can think of it like negative 4x squared. It's going to be like I'm adding 4x. So negative 4x squared plus 8x, because I'm adding 4x and another 4x. And then plus 20 divided by x minus 1 times x plus 5. All right, so in this example, we had to find a common denominator, and the next one we're going to be looking at, it already has the common denominator, so you can just perform whatever operation, whether it's adding or subtracting, for the two rational expressions. I just want to look on here and see. Yeah, there wasn't going to be, if this was able to be factored, sometimes you can run into a scenario where you have a quadratic and then one of the factors is going to be the numerator or the denominator. in our example, we could factor out a -4, but that's not going to be the case. So this looks like a minus 3 plus a minus 1. All of this is over 6a plus 12. So I get 2a minus 4 over 6a plus 12. They want us to simplify the numerator and the denominator. I can factor out a 2 in the numerator to make this a minus 2. I can factor out a 6 in the denominator to make this a plus 3. So simplified, this is a minus 2 over 3 times a plus 3. When I'm multiplying, I'm going to multiply across here. So this is going to be like a minus 2 times 7a plus 21, which I'm going to write as factors and not distribute yet. And I'm dividing by 7 times a plus 3. I can factor out a 7 from the 7a and a 7 from the 21 to rewrite this like a minus 2 times the 7 times the a plus 3 and I'm dividing by 7 times a plus 3. Now I can see the 7 and the 7 are going to cancel here. A plus 3 divided by a plus 3 is gone, and the whole thing is going to be equal to a minus 2. All right, in both 6, I did not do this on purpose, 6 and 7, we are dividing, right? A fraction divided by a fraction. We can, for like number 7 and for 6, multiply by what the least common denominator would be if we were trying to get rid of the fractions. I have an easier time multiplying by the reciprocal, so I can keep this as 9 over x squared plus 13x plus 40 times 7x plus 35 divided by 1. So I'm keeping this part here the same. Instead of dividing, I'm now multiplying, and I'm going to multiply by the reciprocal. So this becomes 7x plus 35. So I get 9 times 7x plus 35 divided by x squared plus 13x plus 40. This is going to be equal to 9 times 7 times x plus 5 divided by x squared plus 40 is going to be x plus 5 times x plus 8. So x plus 5 and x plus 5 are going to cancel. I'm left with 63 over x plus 8. In the same way this last one was division, when I got the what looks like almost a fraction divided by a fraction, here I'm also dividing, so I can write this like 3x plus 1 over 4 times 3x plus 1 over x minus 4. So this is 3x plus 1 squared over 4 times x minus 4. If I had to expand this out, it's going to look like 9x squared plus 6x plus 1 over 4x minus 16. Alright, I'll have more room on the actual test to be able to do the polynomial long division. We're setting this one up here. 9x cubed plus 23x squared minus 19x minus 19. And we're dividing by x plus 3. We take the first term here, the 9x cubed. and we divide it by the x here. You get 9x squared. I'm going to write that in the x squared place here. Now I'm multiplying 9x squared times x plus 3 to get 9x cubed plus 27x. An important thing to remember here is that we're going to divide, multiply, subtract. Now we're subtracting 9x cubed from 9x cubed, and, this should be 27x squared. 23x squared, take away 27x squared. So I get negative 4x squared minus 19x minus 19. Just like last time, I'm going to take my value here, the negative 4x squared, divide it by x to get negative 4x. And then I'm multiplying negative 4x and x plus 3 to get minus 4x squared. Sorry, this should be minus 4x squared minus 12x. And then I'm subtracting. These are going to cancel. If it's negative 19, taking away a negative 12x, it's like negative 19x plus 12x. So I get the negative 7x. I'm going to then take my negative 7x, divide by x, and get negative 7. I'm multiplying x plus 3 times negative 7, which I've not left myself enough room for, but I would take away 7x and then minus 21. And when I subtract this, negative 7x minus a negative 7x is just going to be 0. Negative 19 minus a negative 21 is going to be negative 19 plus 21. So I'm going to get 2. So my remainder is 2, or 2 over x plus 3. All right. In this example here, there's two ideas I need to look at. Taking the square root of the radical of a variable, and then taking the square root of the constant 24. So when I'm looking for numbers that multiply to 24, whose factors are perfect squares, I've gone through and shown you guys writing the pairs of factors here. It can be a little slow and time consuming. Some people have an easier time doing a factor tree, like saying, okay, 24 is 12 and 2, and 12 is 2 and 6, and 6 is 2 and 3. We're looking for the prime factors. So 24 is 2 to the third times 3. The only perfect square here is going to be 2 squared times 2 times 3. Or I would show this like, I can rewrite this like the square root of 4 times the square root of 6. In terms of x squared being a perfect square, I can write this like x squared times x. So I can write this as the product 4x squared times 6x, or the one I could simplify, the 4x squared times the square root of 6x. Now 4x squared I can simplify to 2x, and then the square root of 6x. In number 10, we're looking at the cube root. And remember, we can take the cube root of negative numbers. So running through some of the cubes. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. And 4 cubed is going to be 64. So the fact that our number is smaller than 64 tells me that I need to either be able to find a cube of with 2 or with 3. So it's not going to be 2 cubed. So 27 times 2 is equal to 54. And I'm looking for a perfect cube. When you're finding the cube root of the exponent, it's almost like you're dividing by the index here. So I can rewrite this like, I'm going to keep the sign with the 27. Negative 27 x cubed times 2. Or the square root of negative 27 x cubed times, sorry, this should be the cube root. Make sure you're including the index. So negative 27 x cubed and times the cube root of 2. This is going to be negative 3 x cubed cube root of 2. Oh, sorry. I was writing the wrong thing. I meant to write, this is x to the 6th root, and the cube root of x to the 6th is going to be 2. All right, so when we write each expression in exponential form, I'm trying to write this like 3n raised to the index is going to be the denominator, and the 8 is going to be the numerator. Please make sure you are throwing parentheses around both 3 and n. It's not just 3 times n to the 8/5. Both 3 and n are raised to the 8/5. All right, for number 12, we're going to be going in the opposite direction. Like if I have x to the a over b, I can write this as the radical b with the index of b. Either that radical raised to a or x to the a inside the index of b. I prefer this one, personally, because I think it's easier to not mess up the notation. So I could write this like 7b this is going to be the cube root raised to the 2nd power. All right, I'm going to stop this one here. Email me if you have any questions, and I will see you guys tomorrow.